Thank you for the introduction, and thank you for the conference organizers. Let me see if I can get this figured out. Okay. So my affiliation is kind of convoluted because I'm normally a professor at the United States Naval Academy. So this is in Annapolis, Maryland, just outside of Washington, D.C. I'm on sabbatical this year, so I'm currently a visiting fellow at BCAM, which is the Bass Center of Applied Mathematics. So I'll be doing work in Bilbao for the next 6 months. So what I'm going to be talking about is my general research area in finding simplified models for lots of things, but in particular the MJO, the Madden-Julian Oscillation, as well as other convectively coupled equatorial waves. And it's a funny coincidence that we talked in the earlier talk that reaching back all the way to 2012 was very hard to do, but I'm going to start with a quote from 2012 that I think I might have to retire after this one, because this is one of my favorite quotes about the MJO, because it motivates my research, and it kind of points out the importance of understanding the MJO because it literally affects billions of people. However, in North America in particular, when I give this talk, I can ask the audience, have you heard of the MJO? And if I'm talking to a general math audience, which I tend to do, nobody has heard of an MJO. Atmospheric science is a lot different. I think everybody has heard of an MJO from previous talks today. But the big bolded point at the end, basic physical mechanisms are not well understood. So this is not my words. This is from Randall in 2012. And I would change this 10 years later to say that there's a lot of hypotheses about basic physical mechanisms of the MJO, but not a consensus on them. So that is what I'm trying to do. I'm trying to create a model. So instead of getting a very complex model of the MJO, I want to basically make a lot of approximations, give up a lot of predictability and forecasting to be able to give a simple explanation of the mechanisms. So the game here is to keep things simple. So again, looking at the MJO, we just have a massive storm that usually originates over the east coast of Africa. And this picture just kind of points out the scale. You have tropical cyclones starting to form off the MJO. And the storm is roughly, in this picture, 6,600 kilometers. And then we get the circumference of the Earth. So if I take, this is the peak of the storm. There's dry region about equal in front. You get a storm that is with the dry system about a fourth to a third the circumference of the equator. So that'll come into play later. Okay, so why is the MJO important to non-tropical regions? We've heard from the last talk something called the Pineapple Express, which affects the west coast of North America. And what has been shown is that the MJO can strengthen or weaken this Pineapple Express. So it can kind of intensify these major rain events, plus many other events across the globe, including tropical cyclones in the region. Okay, so we see this nice top-down picture of the MJO. We see the global effects. The question is, how do you see the MJO in data? So one way to do that is to look at the tropical region and rainfall. So I'm going to average over the tropics, usually -15 or 15 south to 15 north rainfall. And then I'm going to look at a Hofmüller. So the x-axis is longitude or your zonal picture. And then the y-axis is in time. And then my preference is to march forward in time going up. So anything moving left to right is an eastward propagating storm. Anything moving right to left is a westward propagating storm. And if something is stationary, I mean, it's just not moving. So if we look at this precip Hofmüller, what you can see are some big green blotches with some red in the middle that are propagating left to right, so moving eastward at a slow speed. And then you see very small eastward propagating things that are much faster because the slope is shallower. And then you will see westward. So what you can do is take the 30-year satellite data at the time and average up all of these Hofmüllers, and then take the Fourier transform in space and time, and that will give you something on this right called the power spectral density. And here you can kind of see the MJO a little better. What do we see is the x-axis is wave number. And the way to digest this is the positive wave numbers are moving eastward. The negative wave numbers are moving westward. And smaller wave numbers means bigger scales. So again, that picture we saw, a quarter to a third of the circumference of the Earth gave us the MJO. And if we look here, wave numbers 1, 2, and 3 have a very large spike. And then the y-axis is the temporal frequency. So this is very slow moving. But you can also see some other features that are maybe harder to see here. So again, how can we see these features a little better? Well, Wheeler-Collattis had a good idea and said, well, everything's sort of decaying in power from the origin. So let's remove that decay and see what's left. And this is the picture that is sort of the tropical waves summarized in one picture. So you have a large power anomaly for the MJO. You have another power anomaly for the Kelvin wave. These are the faster right moving or left to right moving storms that are on a smaller scale. They're on smaller scales because bigger wave numbers. They're faster moving because they're further up in the y-axis. You have westward storms, equatorial Rossbys, and then you have the WIG, which are almost impossible to see in the Hobmolar because they're just so small scales and very fast moving. Okay, so the goal of this work is to develop a unified, simple model that captures all of these things. Okay. So there have been done prior models. There's a ton of simplified models of the MJO. Some of them I've just listed here: boundary layer friction model, moisture mode theories, and a skeleton model by my collaborator, Sam Steckman, on this paper. And then there's been a lot of simplified models on convectively coupled equatorial waves. So we're by no means new to do this. So how do we get the model? Again, we're going simpler is better in our terms. So we start off with linearized 3D equations for rotating hydrostatic Buchanan's fluids. There are no moisture variables listed here so far, but these are sort of the full three-dimensional in space models. And what we're going to do is take a lot of approximations here to get one-dimensional in space and time model. So what are the approximations? We want to capture the MJO. So we make a lot of approximations in the vertical structure here, and we get a somewhat shallow water system. We also want the MJO latitudinally, so we take an approximation there as well. If you do these approximations with just the dry equations, you get a dispersion relation which looks like this. And these lines look familiar because they show up in the power spectral density. So these solid lines, I forgot to mention, are the theoretical lines that are found using these approximations. So you get a Kelvin dispersion curve, you get WIGs and Eastern inertial gravity curves. We didn't see any power for the Eastern inertial gravity. I'll come back to that. And then you see Rossby curves. There's also a mixed Rossby gravity. We don't see this in the previous plot because this is asymmetric. When we averaged over the tropics, we lost all asymmetries. So you can do other observational techniques to find the mixed Rossby gravity. Okay, one important note, there is no dispersion curve for the MJO using just the dry variables. Okay, so what do? I'm gonna take a step back. I'm not gonna go to the full linearized Buchanan's equations. I'm gonna go to a midway point. So we've already done the approximation over the vertical axis. So this is the shallow water system that I mentioned. And now we're going to include a water variable or moisture variable. And then the question is, how do we couple the moisture to the dry variables through the latent heating? So for us, again, simpler is better. So the coupling is that a moisture anomaly is going to cause heating in the atmosphere. And then a moisture anomaly is going to cause a sink in the form of precipitation. Okay. An interesting note is that we tried as much as we could to get the unified theory with one moisture variable, and we could not do it. We had to have two moisture variables, Q low and Q mid. And these moisture variables vary a lot in the variables of Q, tau, Q and tau. So B is your diffusion coefficient. So this is just simple eddy diffusion. We have forcing. Here you should think the forcing is just giving you the mean rainfall, and then stochastic forcing. And the only reason stochastic forcing is used here is to drive the system. If we get rid of stochastic forcing, what happens is that you give an initial condition, you'll see the initial condition decay, and then nothing else. So that the only reason stochastic forcing is used here is to force the system. So we didn't just pick these parameters out of thin air. What we did is the low tropospheric moisture is a sort of Betz-Miller type convective adjustment scheme. So from a Betz-Miller study, they showed that the convective adjustment, so convective adjustment is just how you're choosing the precip as well as the heating. This tau should be around 1 hour. And the Q low has to be a very, so the convergence term is given by this Q low, which can approximate the vertical gradient of moisture. This Q tilde low needs to be chosen in a specific way to get the right Kelvin wave speed as well as the Rossby wave speed. So these are kind of set. Where does this middle moisture come from? This came from previous work from my collaborator, Sam Steckman, and I, where we looked at just a tropical background spectrum with no waves. And in this, tau mid had to be close to 1 day. So these are very vastly different timescales that are working on different sets of the atmosphere. And then this QM, we really didn't know what it should be. So this was kind of the parameter fitting. The nice thing about this model is it's simple. Well, when you look at the zonal waves, this turns into a one-dimensional stochastic PDE, the stochastic heat equation. Short story about that, it's exactly solvable. So all the statistics I'm going to show, this is a linear equation. Again, this confused us because the MJO is often talked about being a nonlinear process. So how are we getting a linear equation to model a nonlinear process? We can solve everything exactly. All the statistics are exact. The only error that comes in is if we're random sampling the white noise. Okay, so how does this compare? Again, we're giving up a lot of prediction and forecasting to understand the mechanisms, which the mechanisms I explained are these two different convective adjustment times between the lower and the mid tropospheric regions, these moisture gradients, Q low and Q mid, and then just including eddy diffusion. Okay, so if we look at the Hofmollers, we get slow propagating large moisture events eastward, which is your MJO. We still get westward traveling Rossby waves, and then we even get the fast moving Kelvin waves. If we look at the power spectrum, the power spectrum is very close. We have this white line here, which is the dry Kelvin wave. So if you get rid of moisture, that should be your dry dispersion curve. I'll talk about that a little bit later. And then if we just look at the anomalies also look very good compared to observed. Okay, so there's a math saying in applied math that all models are wrong, some are useful. So one thing you can ask is there something that this model tells us about the atmosphere that maybe we didn't notice before? Oh, sorry, one more picture about the structure. Yeah, so top-down view of the MJO that's often shown is this picture from Hendon Salby. So you have longitude here, latitude, and then the shading is moisture. The contours are pressure or geopotential height, and then the vectors are winds. And the important things is that you have a moisture anomaly with convergence of winds. You have this quadrupole structure in the pressures, and the winds form gyres around these quadrupoles. So our model has those. Okay, so is there something our model can say about the atmosphere that maybe we didn't notice? So a lot of attention is paid on the peaks of the power spectrum, but at least I haven't heard a lot talked about the valleys. So notice that the dry wave speed has a very sharp valley in our model. And in observations, we also see a valley in the dry wave speed. So could they be caused by anti-resonance? So in my differential equations class, we always talk about resonance, and that's if you have a natural spring, you're forcing it at just the right frequency to cause the spring to kind of compound its amplitudes and grow and grow. Anti-resonance, I encourage you to look up YouTube videos on anti-resonance. You have a coupled spring oscillator system, and you can force one of them so that basically all of the energy gets transferred from the forcing spring to the other spring. So what we did is we reduced our model further to kind of explain this mechanism. So you have all the dry variables U with a certain frequency, natural frequency. You couple them to Q, and then Q is coupled to U in the similar way as our model. And then you're going to force this at some frequency. So with our model, because we're using space-time white noise, it's being forced at all frequencies at the same force. Here, we can just say, let's tune this. So what is the anti-resonance forcing? When is Q 0? So when is the moisture 0? Well, that occurs if we're forcing at the dry frequency. So this is the dry frequency. So what would you see is you would see a spectral valley along the dry Kelvin wave. But if you looked at some of the dry variables, you would see power there. So how can this be used to explain? Well, we saw that the dispersion curve included the western and eastward inertial gravity wave. We don't see any power at the inertial gravity wave. This is just leftover Kelvin. We don't see any power at the inertial gravity wave because the dry Kelvin wave is suppressing that. The valley of the dry Kelvin wave is suppressing that. And then, in the model, why don't we see any westward traveling slow movements? And that's because we have the dry equatorial Rossby waves suppressing any power on that side as well. Okay, so this is a simple unified model of the MJO and convectively coupled equatorial waves. The important mechanisms are these two convective adjustment timescales, tau low and tau mid, and then you just have eddy diffusion. And then this anti-resonance mechanism is something interesting that comes from the model that I've never thought about in terms of observation. So thank you for your attention.
Thank you. So there are some questions or comments.
Thanks, that was really interesting. So in light of what you're saying there, but in the end about the anti-resonance, and so do you think your choice of white noise is quite important? Like if you used a red noise driver, do you think that would make much difference to the results?
I don't think it would make much difference. So if you use red noise, let's see if I have a good picture of it. I don't. So our previous model of the background spectrum, if you basically smooth out this picture, you get something called the tropical background spectrum. And you basically have the max power here, and it decays very quickly in all directions. That would be red noise. White noise is just constant along all frequencies and times. And where are we? Our model for the mid-latitude is basically red noise. So here you can think red noise with an additional red noise. I think it would look essentially the same as long as you have the majority of the power at the origin and decaying, or not even, this says not even decaying. But that's an interesting question. We haven't actually tried it. Intuitively, I think it would give you similar results.
Does the amplitude of D make a big difference there?
The amplitude of D, again, tells you basically how big your anomalies are.
Yep.
So we set D to be relatively similar for the moisture anomalies as well as the wind anomalies.
It just affects the amplitude of the wave. It's not going to affect the dispersion relation at all.
Yes, exactly, exactly.
Thanks.
Sorry, I'm not sure I understood. What happens without the stochastic forcing?
Yes, good question. So without the stochastic forcing, you start an initial condition, say it looks like an MJO, and then the MJO will just decay until the time scale that's corresponding to the eigen mode of the MJO. So we are doing a lot of work with this model without the noise because as we discussed with the previous question, the noise is just sort of driving the system. All of the dynamics are still captured if you remove the noise. It's just, it doesn't make for the pretty plots, right? Yes, so that's a great question. And this is part of the model that because it decays, because we want to include the stochastic forcing, all of the modes of the model must decay. If you don't, then everything will explode. So then the question is, how would you change the model so that you do not need the stochastic forcing, and therefore you could have some modes that could be self-sustaining? And so this has been something we've been trying recently, introducing nonlinearities to get rid of the stochastic forcing, and we haven't found a simple way to do that. But yeah, that's a very good question.
Other questions?
Yeah, I'm confused about the stochastic forcing too. How is it related to the time scale? I mean, is there anything you tune here to get the time scale, or where does the time scale come from?
The time scale of the stochastic forcing?
No, the time scale of the MJO.
Yeah, so that's a great question. So the time scale of the MJO is, for this model, is a bit longer and slower than seen in observations. But these two time scales are set. The eddy diffusion time and spatial scales are somewhat set by the power spectrum's decay. So Q tilde is also set. So this, which corresponds to middle tropospheric temperature gradient, vertical temperature gradient, controls everything else, including the time scale of the MJO for this model. And it's very hard to understand the perturbations of this value and what happens to the entire model. So, I mean, you still get an MJO. What you can do is play with this model, and this is what we want to do in future research, is you can lower this Q tilde mid. The MJO has roughly the same speed and structure, it's just much weaker. So does this capture a different regime when the MJO is maybe not as active? That's a good question. Yeah, I hope that answered your question.
Okay, another question? I have a question myself. Could you say something about what is the improvement, or so you mentioned several models, previous models of the MJO. So what's the thing? Why do you think this is improving the situation or the understanding of the phenomenon?
Yeah, great question. So the improvement on this model is that a lot of these models don't include, so a lot of these MJO models don't include the convectively coupled waves as well. So the Kelvin, the Rossby, and the WIG. The skeleton model does. A difference between ours and the skeleton is ours is linear. The skeleton model contains a non-linear interactions, and it also contains an extra variable. So another interesting thing is they needed an additional moisture type variable that included a convective amplitude packet, sort of. So ours,
convective activity or something like that.
Yeah. So our model is just two moisture variables and linear.